wanted to kind of do something different for the rest of this because I want to start preparing for my next sort of longer project. I'm still working on getting the four-dimensional Pong video put together. But the next project I'm going to do is going to involve some quantum mechanics, probably quantum computing, but I'm still figuring out exactly what I want to do there. And quantum mechanics involves working with complex numbers, and a lot of people are afraid of complex numbers, or they haven't seen them in a long time, or they don't understand why they should care about imaginary numbers. And so I just wanted to run through my usual spiel for why it's important, why complex numbers are important, why it's worth understanding them, and kind of the basic things that you should remember about complex numbers. And I'm probably going to put this up on my YouTube also, just as a reference, and because I like this particular demonstration of it. People come at complex numbers in a bunch of different ways, and there are a lot of different some people are sort of just interested in it as a mathematical curiosity. You learn it in school, and at least in the US, they teach it as a mathematical curiosity. Essentially, they, as far as I can remember, until I was studying math in university, I don't think anybody ever justified or gave any reason to study complex numbers. I guess when you're doing roots of a polynomial, that's the one time it comes up. So if you do the Pythagorean theorem, or not the quadratic formula, rather, you get two roots, and sometimes one or both of them will be imaginary. And so complex numbers came up there, and I guess we talked about them a little bit in grade school there. So mathematical curiosity, that's fine. They also come up in graphics, so people might know that they they can be used for rotations in 2 dimensions really easily, and the generalization of complex numbers can be used for rotations in 3 dimensions, so that's quaternions. So sometimes people know them from that. If you do electrical engineering, if you do quantum mechanics, if you do pure math, you learn a lot more about the complex numbers and how useful they are. But I actually like, and we're going to end up using them for something quantum mechanical in a couple of streams, but I actually like motivating it instead by talking about trigonometry class. So at least in the US, you spend 1 year, I think 11th grade, doing trigonometry. Is essentially, it's called algebra 2, I think, a lot of the time, but it's essentially trigonometry class. And the main thing I remember from trig class, and I liked math and I was okay at it in high school, but the main thing I remember is how sine and cosine work, and then having to memorize a huge number of trig identities, just like sum angle formulas and product angle formulas and half angle formulas and double angle formulas. And I was kind of vaguely aware that a lot of them could be derived from each other. So like you learn things like, sine squared plus cosine squared is 1, and things like that. And then you can work out you can divide through by cosine squared, and you get something with tan in it. And I was kind of vaguely aware of that. But it was a lot of memorization. And I don't really like memorizing things. I think memory is great. I think some people have memory is a great gift, and some people are really good at memorizing things. I watch Jeopardy. I like pub trivia as much as the next guy. I like knowing things. But I don't like carrying around redundant things in my memory if I don't need to. And I especially don't like carrying around things that I have to memorize, but they don't help me understand. So I'd like to, memory is a finite resource. I would like to use it on things that are important to remember and then actually like explain something about what I'm trying to study. So I don't mind remembering that the definition of sine is opposite over hypotenuse. I don't even remember that actually. If I'm being honest, I look at a unit triangle in my head or a unit circle in my head. But I don't mind having to memorize that because that's like a reasonable definition of what sine is. I really don't want to have to remember that, you know, sine of theta plus plus what the double angle formulas are like sine theta plus phi is some complicated trig thing. I don't want to remember that. Nobody should have to remember that, because if you learn a small number of things about complex numbers, then you get this for free. There's a really, really straightforward way to work out all of the trig identities that you want, and you never have to memorize anything. Or I guess you do have to memorize something, but you're not really memorizing it. You're learning what complex numbers are and why they work. And that's a much more powerful thing to remember, because now, you know, when you show up at a electrical engineering class or you learn quantum mechanics or somebody's teaching calculus, all of that stuff is reusable, whereas I don't really remember ever using the double angle formulas after trig class. So that's what I'm going to run through, is basically the things to know about complex numbers. Some of them are simple, like the square root of -1 is I, which is the defining property, and we'll talk about in a moment. Some of them are more complex, and they're also derivable, but you need a little bit more of a background, and it's easy enough in high school. They should just teach it as a rule, and that would be fine. So I'll run through that. We'll do some examples, and then work out what the sum angle formulas are, because I don't remember them. And we'll do some tests to make sure I'm getting it right, and you'll see kind of how easy this can be. And then it'll make a lot more sense in a few days when I'm talking about quantum mechanics and we've got complex numbers bouncing around. It will be useful to return to that. So, complex numbers. What is a complex number is the first question, and the answer is it is a number z, such which is the sum of a real number, so 5, and a product of some other real number and the complex number I, or the imaginary unit I, where I is the square root of 1. So maybe I'll just do this in comments. So z is some real number, plus some other real number times I, and I is the square root of -1. And why is this important? Why is this a thing? Well, in the real numbers, you can take square roots of positive numbers and you'll get back real roots, right? The square root of 9 is 3, but also -3 squared is also 9. So really there are sort of 2 square roots of 9. There's -3 and 3. But it's possible to imagine, and if you ask what the square root of a negative number is in the reals, it doesn't have one. That question doesn't make sense in the real numbers. But it's possible to imagine that there is such a number, right? We can just define, we have this square root function, we know what it does for positive numbers. We can just define what it does for negative numbers, and call that a new number. And the reason we use -1 is that then the square root of -1 defines all of the other imaginary numbers, right? So now if we want to know what the square root of -7 is, Well, it's the square root of -1 times 7, which is the square root of -1 times the square root of 7, which is I times the square root of 7. And we don't, I mean, this is some awful decimal between 2 and 3, but we could do it. So you only need to define one new object, one new number, and then all of the others just fall out of the math from there. And there are reasons that we might want to do this, but the way that I would usually teach this is to just say, look, this is the rule, right? We have real numbers. We know real numbers. We can work with them. We can add. We can multiply and divide. We can take square roots of positive ones. And I'm just telling you, there's a new rule that you can take the square root of -1, and we're going to call it I. And that doesn't break anything. There's nothing wrong with doing that. I tell you I'm going to do that. You can't stop me, right? This is not the same thing as defining a new number. Whatever, alpha as 0/0 or something. If you try to do this, it breaks math, right? Because you start to be able to do crazy stuff with arithmetic, where you can break arithmetic. Namely, something like alpha equals 15, like 2 alpha equals 15. If you then multiply the zeros out, so you'd have 2 times 0/0 is 15, which means that 2, well, that's not quite the right example. There are examples of this that break math. I can't quite work out what they are, but they do. It's a problem. There is no similar problem for I. Everything just continues to work out, and in fact, in some sense, it works out better. So in particular, all polynomials, all of their roots, no matter how big a polynomial is, doesn't just have to be squared, but it could have to the 5th, to the 10th, whatever. All of their roots will be in the complex numbers, which is neat. The second thing, so let's just go ahead and write some actual tests here. So let's say, let's let z be complex 5 and 2. So 5 times 2i is the idea here. And we can say, let's assert that the real part is 5, and let's assert that the imaginary part is 2. So this is 5 plus 2i, and this is just saying that the real part is 5 and the imaginary part is 2. Let's also note that we can add complex numbers together. So we could have -3 and whatever, 14.5, and we can assert that z plus w is the same thing as, so we just do it coordinate wise, right? Because this is just a number. It's just like in ordinary math, right? If this was just 5 plus 2x, doesn't matter that it's I. If it were just x, if it was whatever, what can you do? You can group like terms, right? And so this is just 5 minus 3, and we add the imaginary parts, which is 2 plus 14.5. Being really inconsistent with my significant figures here, but with my decimals, but that's fine. Okay. So that should be true. We can also subtract complex numbers. It's the same thing as adding a negative of the complex numbers. So let's do this. And we can multiply complex numbers by scalar factors. So we could have 7 times z, which would be 35. So again, it's just the same thing as if I were any other were variable, right? It's almost as though you don't know what I is. You just distribute the multiplication through. So 7 times 5 is 35, and 7 times 2 is 14. So this is 35 plus 14i at the end of the day. Okay. And you can also multiply complex numbers themselves. So in this case, we could say z times w would be, and here it's a little bit trickier to calculate, but you just FOIL them, as at least that's the acronym used in American schools. You multiply all of the different parts together, just like you would with polynomials, for instance. So in this case, it's going to be, well, let's do it on the side first. So we're saying 5 plus 2i times negative 3 plus 14.5. I've given myself somewhat harder ones to do than I could have. So that's minus 15 is the first two, minus 6i, minus, plus 14.5 times 2 is what, 29? So plus 29i. And then there's one tricky bit. Oh wait, I didn't do that right. Sorry. So 5 times negative 3 is negative 15. 5 times 14, or 2i times negative 3 is minus 6i. 5 times 14.5i is what, 29, 58, 68, 72.5, I think. Gonna have to check that. And then 2i times 14.5i is, and this is where it's a little bit tricky, is 29 times I squared. And I squared is negative 1 because it's the square, I is the square root of negative 1, right? And so let me actually pop this out. And so this becomes negative, and we have minus 15 minus 29 plus minus 6 plus 72.5 I. And that, I really gave myself, I should have picked smaller numbers. I'm not particularly good at head math. Is what, 44? I say not particularly good at head math, if I'm being honest. I'm bad at it, so it will be kind of miraculous if I get all of this right. And that's 66.5i, I think. Okay, so that's minus 44 and 66.5. It is a myth, by the way, that you have to be good at head math or really doing arithmetic at all to be good at math. It is not true. Some people are, but you certainly don't have to be. Okay, so you can multiply complex numbers, and you just follow all the same rules that you usually would, and all you have to do is remember that the I squared is -1 because the square root of I, the square root of -1 is I. So those are the basic operations. The other thing that you should know is that complex numbers can be represented as on the plane as a two-dimensional thing. So we're carrying around, we're saying 5 plus 2i, we're saying 35 plus 14i, we're saying minus 44 plus 66.5i. You can plot these in two dimensions because you have two numbers, right? So you can plot the real number on the x-axis and the imaginary number on the y-axis. It's useful to plot things. It's useful to visualize things. It helps us understand them. We're really good at seeing the world, and so you can do that. Let's just say gets coordinates. I'll just do it in the previous test. So we could do z dot get coordinates, and this would just be whatever it is, 5 and 2. Okay. When you plot them on the, and just as to show what that looks like if people haven't seen it, it looks like this. So you take something on the, just jump into the complex numbers. Yeah, you take something on the x-axis, you plot A. On the y-axis, you plot B. Super simple, but it's useful to do. And notice that addition then becomes basically the same thing as vector addition, if you're familiar with that. And so all you do to add multiple vectors, I don't know if it shows it here somewhere, no, it doesn't, is you take, you've got one complex number out here somewhere, you stick the other complex number, you put its tail to the head of this vector, and you follow it, and the resulting point gives you the resulting vector. It's a nice sort of interpretation of imaginary addition. There is another way to plot complex numbers, or to plot them in two dimensions, to think about complex numbers, maybe is the right way to put it, and that's in polar coordinates. So rather than thinking about them sort of rectangularly as we're this far on the real axis and we're this far on the imaginary axis, you instead think of them as we're this far from the origin, we're this far from 0, 0, call that r, and we're going to rotate, we're phi, here, Greek letter phi, around that's the angle from the real axis. And the nice thing about doing this, I mean, it's just another representation of the same thing, right? So this is both x plus iy, and it's a function of r and phi. And the application will tell you which one you end up using. Sometimes it's convenient to talk in terms of x and y. Sometimes it's convenient to talk in terms of r and phi. This makes sense, right? If you're talking about a planet orbiting a sun, in all likelihood, it's going to be useful to talk in terms of r and phi, right? What are the relevant things as a planet orbits a sun, or as a camera rotates around, right? Anytime you hear rotates, you should think in terms of polar coordinates. And so this more polar representation is um, is and it's very efficient in the complex numbers. It's really easy to do calculations with this polar coordinate in a way that it's not in the real numbers. So in the real numbers, you have to do all of this awful sine and cosine stuff. And it involves a graphing calculator or a trig calculator. And in the complex numbers, it's really much simpler to work with rotations, which is why it ends up being useful, and it's also why this argument is going to work. Right? It's why the trigonometric formulas just fall out of complex numbers. So these are called the polar coordinates, and in particular, they are called the what are they called? The modulus and the or the absolute value. So let's just say absolute value or the magnitude. There are a bunch of different names for it, to be honest, but I'll call it the I think I'll call it the modulus. Magnitude is the best word for it. It describes what it is. And the modulus, or the magnitude, is just the Pythagorean theorem, right? So if you want to figure out how long r is, you do x squared plus y squared, and you take the square root. It's the Pythagorean theorem. So that would be 5. Let's see here. These are going to be F32s, so 5 and 2. Is that how this works in Rust? I think it's this. 5. I think it's this, but it might be. I'm getting my languages confused. Sure. 5 F32. That's just POW. POW F. Raises a number to a floating point power. That's not what I want. I want to raise it to an integer power. Is there POW I? Okay, there we go. Probably should look that up rather than just slamming particular options until the compiler lets me do it. But okay, so it's 5 squared, and now I'm just gonna get rid of that and just do it this way. Plus 2 squared. It reads better. And we'll take the square root of that. Okay. Have to tell it that it's an F32, and then it works out all the other ones. Cool. So that's the magnitude of the number. That's how far it is from the origin, and that's going to be important. And then the other piece is the argument, or the phase of the number. It's usually called the argument. It's not my favorite name in the world, but it's called the argument more often than it's called the phase, so let's just roll with that. And this one, so the answer to this one is a trig question, right? So you're looking for this angle here. That's going to be the tan of x over y, tan of the real part over the imaginary part. So 32 over 2. And then we need to tan it. And there's a thing here where the negative signs need to work out. Like tan will at some point become negative and the argument might not, and I forget how that works. So I probably should write some additional tests there, but it's not going to matter. This one's always going to be positive. There are conventions around how you want to do that. I guess I should write it. I don't want to do that right now. Okay, so these are, other ways to think about the complex number. But the powerful thing is that this polar representation gives us a really nice interpretation of multiplication in the complex numbers. And in fact, it's going to end up working the other way around. This interpretation of the thing that multiplication does, which is rotate things in the complex plane, is what makes it so powerful to use complex numbers in all applications. So anytime that you ask, why are complex numbers showing up here? The reason is, in some sense, there's a circle or a rotation underneath the surface, or maybe it's really obvious. So, for instance, in quantum mechanics, you think of a photon traveling its electromagnetic wave. It has a phase, right? It has how polarized it is. That polarization can be modeled as a complex number because it's a rotation, and it's very convenient to do it that way. And so what is that interpretation? Well, if you take z times w, then what you will do is multiply the magnitudes together and add the arguments. So if we look, does it have an image of this somewhere? I should have found some images somewhere of this beforehand. Let's see here, can we say complex multiplication? Nope. Okay, well, we'll just do it. So for instance, and I'm going to define 2 new complex numbers down here, because I want to be able to say complex polar. So if we make the length, the magnitude of the complex number 3, and the argument, so the angle, tau over 8, 45 degree angle, 45 degrees. Do I have to import this? Okay. And we do the same thing for w, but let's make it -2, and tau over 6. Then the product, z times w, should be, so product, the real part of the product, the magnitude of the product is going to be the magnitude of the real parts. So z dot magnitude, or the product of the, the product of the magnitudes. I'm typing and speaking at the same time, which is always risky. When I was a kid, I used to be typing my homework or something, and my mom would call me for dinner, and I would come back home at the end of I would come back to my homework, and it would have, like, come to dinner written in it, because I can't type and think at the same time, apparently. So the product, so the magnitude of multiplying two complex numbers is the product of the magnitudes. The argument is the sum of the angles. And I'm going to mod this by tau. By the way, if you don't know what tau is, it's just 2 pi. It is easier to think in terms of tau than it is to think in terms of 2 pi, because tau over 8 is just an eighth of the circle. Tau over 6 is just the sixth of the circle. Makes it easier for me to think about it. Okay. But this is really powerful, because what we're getting is a really nice way to represent rotations in terms of complex numbers. If you want to rotate something, you multiply it by something with that argument. You want to rotate by 30 degrees, you pick a complex number that's 30 degrees that has an argument of 30 degrees. That's easy to do. And if you don't want to change its magnitude at all, you just make the magnitude 1 when you multiply it. And so if you multiply the point on the unit circle, right, if you go find, if you take your polar representation and you draw a unit circle, let's say that this is 1, and you go 30 degrees around the unit circle and find that number, which is easy to do. Now, anytime that you multiply a complex number by 30 degrees around the unit circle, what you're doing is rotating by 30 degrees. This is really, really powerful, and we'll see why in a moment. Cool. So let's go ahead and actually implement this type. Do I want to implement this type, or do I just want to import it? Maybe I should just import it. Let's just import it. So let's just import it. Num complex. Use num complex. Okay. And so now there are going to be a whole bunch of things that I came up with names for that are going to be named somewhat differently. For example, .re, .im. This is all fine. This needs to be a float. Is there a coordinate? There's 2 polar. There's no coordinate function. That's fine. Get rid of that. We want the magnitude. We want the absolute value. Okay, so they use absolute value. That's all right. And what do they use for the angle? They use arg. Okay. For the argument. And then can I say from polar? I sure can. And from polar. Okay, that's not bad. And let's just make sure. Yeah. Cool. And then these just become .abs, abs and arg and arg. Oops. Let's not cargo test. Let's test this particular one. Okay, what did we do wrong? Do I have my tan backwards? Probably. Oh, no, I don't. Negative isn't backwards. So the argument of 5 plus 2i should be, oh yeah, tan of 2 over, yeah, I got that backwards. And still not right. Oh, it's got to be the arctan. It's not. So the tangent is the ratio of opposite over adjacent. The arctan is what you use to get the angle back from the ratio. Keep trying to cargo test. All right, let's cargo test this. And what else you got for me? Okay, we're getting floating point issues. That's logical. So we can just change this. I really would like for Rust to have built-in approximate equals assertions would be really nice, because it's kind of clunky and to do it yourself, and the error messages are not great. I know there's a crate for it, but then I have to go find the crate, which I don't want to do right now. Which one is this? Hey, everything passes. Okay, so what I told you is true, except for I messed up the order of tan and that it needed to be the arctan. But I was close. And now you believe me because the computer told me it was right. I did manage to do all of my arithmetic here correctly, which is frankly remarkable. Okay, so those are the rules. Those are the things you need to know. I is the square root of -1, and when you multiply complex numbers, you multiply the magnitudes and you add the arguments. This is one other thing that you need to know, which is that in order to write down the polar notation, let z polar, what you say is the magnitude of z, so the magnitude of z times e to the, and this is going to work in Rust, so I will write it here. It's going to be the magnitude of z, which is denoted like that, times e to the I, and then the argument of z, which is, let's just call these r and phi, times phi. So e here is Euler's number. It is 2.7 something something something. Similar to I, it does not matter. Like, knowing what the value of it is not the important part. You should just interpret e to a complex number as a rotation by whatever's multiplying, or e the imaginary number rather, as a rotation by phi. So e to the I something is rotating by that something, and then we're multiplying it by another real number here. So that is going to be the magnitude of z times the argument of z. So we'll need a new complex number here, which is just the argument of z. And then we want to exponentiate that, or we want to I don't want to exponentiate it. I want to raise it to the eth power, or take e to it, rather. How do I do that? How do I do that? Probably .exp. I'm guessing is e to the arg times I power. It's a little clunky in Rust notation. Maybe the easier place to see it is here. So z, the complex number overall, is r times e to the I phi. And it's just e to the I phi is rotate by phi. R is just the length of the thing. And this makes sense, right? Because e to the I phi is, I'm telling you, it's rotate by phi. So it's that number I was talking about before that's on the unit circle that's rotated by phi. And then when you multiply that by a real number, which has angle 0 and magnitude r, you've now rotated by phi and you've extended to r. And that should get you back to z. And so let's make sure that that's the case. Let's assert that z minus z polar is really close to being the same thing. And it is. So hopefully you now believe me that this is the formula for polar coordinates. And that gets us all the pieces we need in order to work out the sine, the double angle formulas, the added angle formulas, and so on, to our heart's content. Because we can write that same formula, r times e to the I phi, in terms of trig. So let's do a new test. And let's just test trig identities. What we want to note is called Euler's formula, which is that, so if e to the I phi is a rotation around the unit circle by phi, then we should be able to write that in terms of trig, right? Because, well, this is just a right triangle, and so if r is 1, because we're leaving r off of this is just a rotation by phi. So we're assuming r is 1, then what are the real and the imaginary coordinates of this? Well, they're just the cosine of x plus I times the sine of y, because r is 1, and so it drops out of the ratios. So let's write this down and check this. We're going to have cosine of phi plus I times the sine of phi. And that's true, that has to be true, because that's what sine and cosine are, right? If you look at a unit circle, and you've gone some angle around it, cosine gives you the x coordinate and sine gives you the y coordinate. That's the definition you should think of cosine and sine. You shouldn't really think of ratios. But if you want to think of ratios, what is the cosine of phi? Well, it's adjacent over hypotenuse, which is x over r, and times I times sine of phi is opposite over hypotenuse, which is y over r. But r is just 1, because we're on a unit circle. So this is x plus iy. But that's what we wanted to begin with. And in fact, we can put an r in front of this, and put an r in front of this, and nothing changes. If we want to. So I'm actually not going to do that because I think it confuses things further, but you can carry an r through. Okay, so why this should, if you remember that this is what it means to rotate in complex numbers, then this picture should be what you have in your head, and then this formula is not something you memorize, right? This formula is just something you read off of that picture in your head, which is what I did in order to recall it. I don't memorize this formula. I memorize the idea of that picture. I remember the idea of what raising something to an imaginary number is. It's rotation. And once you have this, you can get all of the trig identities that you want. So, for example, if you want the double angle formula, if you want the sum angle formula, that means that you want like cosine of theta plus phi of theta, and sine of theta plus, cosine, I'm talking and reading now, and that's causing problems. So we want to know sine and cosine of phi of theta, let's say. Nope. One more time, Chris. We want to know sine of phi plus theta and cosine of phi plus theta. Those are the sum angle formulas, I think they called them when I was in high school. And I memorized these, and I kind of vaguely remember what they look like in my head. They're annoying because one of them they're both sums of something, and one of them is sum of sine times cosine and cosine of sine, and one of them is sine, and cosine, and one of them has a minus sign in it somewhere. And, I just memorized it at the time. Instead of memorizing it, though, you can notice that if you put phi plus theta into the right side of this, you're going to get a expression on the left side of this that you can do arithmetic on much more easily, and you already know how to do that arithmetic. So let's do that. So cosine of phi plus theta plus I times sine phi plus theta. That's the right hand of this, but with phi and theta stuck in instead of phi. And that has to be equal to e to the I phi plus theta. We know this to be true. This is just Euler's formula. This is just the left side. By Euler's formula. Except that we know how to deal with, because we know what to do with sums of exponents, right? So we can say that this is e to the I times phi theta times e to the I times theta, right? When we have exponents if you have an exponent that's being added, that turns it into multiplication when you bring it outside of the exponent. And e is just a number, and we're just exponentiating it. We haven't done anything wrong. We're just following the rules of arithmetic that we know and love. Okay, but we know how to expand these now. Again, by Euler's formula, this is cosine of phi, need some parentheses, cosine of phi plus I times sine of phi. And that's being multiplied by cosine of theta plus I times sine of theta by Euler's formula. Again. Okay, well, now I know how to multiply these. I can FOIL them out, right? Cosine theta plus, let's make sure I do this right, I times cosine of phi times sine of theta plus I times sine of phi times cosine of theta plus I squared, which is going to be -1, times sine phi sine theta. And that is, let's collect like terms. So we're going to collect the real terms, which are cosine phi times cosine theta minus, because of that I squared is -1, sine theta. That's the real term. And then the imaginary term is cosine of phi times sine of theta plus sine of phi cosine of theta. And this seems ugly. I don't know where that parenthesis came from. Except I'm already starting to recognize and have flashbacks to high school trigonometry. These are the formulas I'm looking for. Because if we started all the way up here with something real plus something imaginary, this is not going to become, these are sine and cosine of real numbers. These are real numbers. This is a real number. This is sine and cosine and addition and multiplication of real numbers. That's going to stay a real number. We're multiplying it by I, so it's going to be imaginary. So we can split this out. We can say, okay, these are equal to one another, so the real parts must be equal and the imaginary parts must be equal. And that means that cosine of phi plus theta is this. I can get rid of a layer of parentheses. And sine of phi plus theta is this, the imaginary part. And if I did my algebra right, which I can check in a moment, then these are the formulas I was looking for. This is what I wanted to know at the beginning. But it falls out of this this multiplication that you do here. And cosine minus sine, cosine sine plus sine cosine. And I'm pretty sure I did it right. I'm pretty sure this is the right answer. One thing we could check is if sine and theta are both 0, or sorry, if phi and theta are both 0, then we need to get, this would be cosine of 0, we need to get a 1 back. And indeed, cosine of 0 plus cosine of 0 is 1. So you multiply them, it's 1. And the signs are 0, so this whole thing equals 1. That's good. And for sign, there's going to be a sign of 0 in both of these terms, and so they're both going to be 0, which is what you want. So that makes me pretty comfortable that I derived it correctly. And in fact, I don't even need to be that comfortable. Like, if this seems like a lot of work, it's because I'm explaining it step by step by step by step by step. But if I needed this, like if someone walked up to me tomorrow and said, you don't get the internet, tell me what the sum of, some phi and some theta are, I would not write down all of this. I would write down probably what would I write down? I would write down this just to make sure that I get Euler's formula right. And then I would do all of this multiplication in my head, because after you do it a couple times, you get really good at working out what all of the pluses and minuses are here. And I'm not good at head math, as we've already established, but this is not hard to do in your head once you've done it a couple times, and it's a lot easier, especially if it's years later. It's years between when I use this stuff, which it might be. I usually only teach this to my students once, and then they know it, and I don't have to ever teach it again, or I don't have to teach it to that student again. And so, it's much more sustainable to remember this, because I do think about complex numbers. Much more sustainable to remember that, and to be able to, in 2 steps, write down these formulas, and then I can use them. And by the way, you can derive all of the other ones from here also. If you want the angle difference formulas, you just make theta negative, and you just do the arithmetic. Or if you want the double angle formulas, you just make phi equal to theta, and you do the math, and they all drop out. So these are the main ones that are worth knowing how to derive, and then all of the others are just kind of special cases of the original ones. So I flippantly, the thing I always tell people is, like, an entire year of math class in the US can be taught in an hour, which it's been about an hour, so I think I nailed it. And you really don't need to remember very much in order to get all of these formulas at the end of the day. Cool. Stop talking there for a moment, see if anybody has any questions. Hey, Commander Thrashton, how's it going? Going through the basics of complex numbers, because the next project I'm going to jump into is going to have to do with quantum mechanics and perhaps quantum computing. I'm still working out exactly what it's going to be, and it's definitely going to involve some complex numbers. So wanted to go through the basics and have some tests of the complex number library in Rust, because I actually had not used it before, so wanted to write out some tests. So I should actually turn this into a little test, I think. Assert, and we can just pick some, let's say phi is tau over whatever, 5, and theta is tau over 9, doesn't matter. Then phi plus theta cosine is the same thing as phi cosine times theta cosine minus phi sine times theta sine. And what don't we like here? point. Let's compare floats. And same thing for the sine example. So sine should be cosine sine plus sine cosine. If I did that right. And there we are. Okay. Cool, cool. So those are basics of complex numbers. Again, just to rehash it, the things to remember are I is the square root of -1. Complex number is written as a plus bi. You add and multiply complex numbers just like you would add and multiply anything else. And there's this way to interpret multiplication. Well, there's this way to write down a complex number as polar coordinates with the absolute value and the argument, where the absolute value is the length of the vector in the complex plane, and the argument is the rotation from the real axis. And then multiplication becomes multiplying the magnitudes together and adding the arguments. And just mathematically, that's super useful because you can really quickly and easily derive things like trig formulas from it. But it's also the reason that we use complex numbers to model rotations in quantum mechanics, in computer graphics, in electrical engineering, and all that good stuff. So it's good to know how to work with these, and it's really not difficult to work with them. There's nothing strange it's a little abstract, but you just follow the rules. You just play a game where you know the rules. There are a couple additional rules, and everything works out.